Now you might be asking at this point in time, how are we going to use these things and why are these important to an operations class and from my perspective as a business student? Well, we're getting there. We got to do it a step at a time, and the next step is probably the single most important mathematical theorem that I know of in business. It's called the central limit theorem, and it's going to help us bring all these things together. Now, in statistics, I'm sure you've discussed the central limit theorem, but I want to put it in the context of an operations application. And maybe the best way to start with talking about something so seemingly esoteric as a theorem, a mathematical theorem, is to use an example that everybody's familiar with. So let me go ahead and just put the title here, central limit theorem, and use Amazon as an example of an application of the central limit theorem. So I want you to imagine a situation where, unfortunately, I have to again draw the United States. And as I told you before, I'm okay at parts of it, I'm less okay at other parts. This looks a little better, I guess. I want to ask you this question. Suppose we had two choices. I'll do choice one in black, and we hold all of our inventory. I'm going to use triangle for inventory, and I'm going to use this to be Amazon. And we're going to hold all of our inventory that we're going to sell all across the United States of books in one centralized location in the United States. And I want to compare that inventory, the efficiency of that inventory, against, let's say, the Barnes & Noble's example, where we have multiple bookstores spread all across the country. And so I'm not obviously going to draw the 2,000 Barnes & Noble's bookstores that are around the country, but I'm going to draw a whole series of little small triangles spread around the country. All right? And remember, the small triangles are going to be Barnes and Nobles. Now here's the situation I want you to consider. Imagine that this country is full of all of the little blue triangles. Suppose Amazon and Barnes & Noble's had exactly the same total customer demand. Let's make it easy. Amazon sells 1 million books per month, and Barnes & Noble's in total also sells 1 million books per month. But Amazon does it in one location, and let's say Barnes & Noble's, to make the numbers easy, Barnes & Noble sells it across 100 locations. Here's the question I have for you that I'd like you to think about. If I'm going to sell exactly the same number of books of exactly the same number of titles, who needs more inventory? Amazon selling 1 million books per month across one location, or Barnes & Noble selling exactly the same volume across 100 locations? Who needs more inventory of books stored up? They're both satisfying the same demand. Now, a quick analysis of this, if you don't understand what the central limit theorem actually tells you, might be there's no difference. As long as the average demand for Amazon is the same as the average demand for Barnes & Noble's, and the average lead time that Amazon has from its suppliers is the same as the average lead time that Barnes & Noble's has from its suppliers, an overly simplistic answer might be there's no difference. The amount of inventory we need is the same. Turns out that's not at all true. It turns out that through something called risk pooling that's going to be described by the central limit theorem, the amount of inventory that Amazon needs is quite a bit less than the amount of inventory Barnes & Noble's needs, because Amazon has all of the demand summed together at one location, whereas Barnes & Noble has the demand split up against 100 locations. And even though on average they're the same, the variability is not the same. The uncertainty of demand is not the same. And thus, the amount of inventory is not the same. In fact, I can tell you right off the bat that we'll see with the central limit theorem later, I can tell you that the amount of inventory that Amazon needs relative to Barnes & Noble's is going to be on the order of 1 over square root of 100, or 1/10 the inventory. And that is because the amount of inventory you need is governed by the variability, and the variability is governed by the square root of the number of locations. So I tried to motivate the usefulness of something like the central limit theorem just a moment ago by talking about risk pooling as it might occur in inventory management, and comparing Amazon to multiple stores like Barnes & Noble. I think we have to get a little bit into the details of the central limit theorem, enough so that we'll be able to apply it rather than just conceptually understand it. So bear with me for the next few minutes as we kind of go into a bit more detail of the central limit theorem. Before I write this down, let me actually write the title down, and then we'll go from there. Again, it's called the central limit theorem. I need to address those of you who are kind of math buffs. What I'm about to describe is actually a variant of the central limit theorem. I'd like to call it the almost true central limit theorem. It's going to relax some of the assumptions that were probably applied when your statistics professor talked to you about the central limit theorem. But it's going to be more useful. It's going to allow us to solve lots of interesting business problems. So keep that in mind, math people. This is an approximately true central limit theorem. It's not the exact form. So first of all, let's write it out. The central limit theorem says this. This is going to be quite mathematical, but bear with me. Let x1, x2, up to x sub k be independent random variables. Okay, x1, x2, x3, all the way up to x sub k are independent random variables. And then let's create a sum. Let's let y be the sum of all those random variables. It's going to be x1 plus x2 plus ... plus x sub k. And let that be a number that we're interested in. I'd like to know how y behaves, which is the sum of each of those x1 plus x2 to xk random variables. Furthermore, suppose we understand something not about y, but about the underlying x1 through xk random variables. So let mu1 and sigma1 represent the mean and the standard deviation of random variable 1, and mu2 and sigma2 represent the mean and the standard deviation of x2, so forth. Mu k sigma k be the mean and standard deviation of x1, x2, ... xk respectively. Okay, so these are the three conditions of the almost true or approximately true or most usefully true central limit theorem. Let x1 through xk be independent random variables. Let y equal the sum of them. And let the mean and the standard deviation of each of those random variables be known. Then, in the limit, as k goes to infinity, so as you sum more and more of these things together, we know that y sub k is distributed as a normal distribution whose mean, mu of y, is simply equal to the sum of all the individual means, and whose standard deviation, sigma of y, is equal to the sum of all the sigma I squareds square root. Now I'm going to pause for a moment and let you look at that before we have a conversation. Now what's this telling us? What are the things that are important about this? Well, what this is going to tell us is several somewhat surprising outcomes. Thing number one it tells us is when you sum up random variables, the resulting sum is a normal distribution regardless of what the individual random variables are. The sum is normal regardless of the form of the x sub I. Let me explain that a little bit more. Notice, nowhere in this statement did I say random variable x1 needed to be normally distributed. I don't care what x1's distribution is. It can be whatever distribution it wants to be. The same goes for x2, x3, all the way up to x sub k. Regardless of what their underlying distribution is, when you sum them together, under certain circumstances, when you sum them together, you get a normally distributed uncertainty range. That means it looks like a normal distribution, more or less, as long as you sum enough of them together. What's another thing that's interesting about this? This one is less interesting because it's probably more intuitive, but look at this statement down here. It says y sub k will be normally distributed, that's 0.1, and now we know the mean of the sum, remember mu of y is the mean of that sum y, is simply the sum of the means. So the mean of the sum is simply the sum of the individual means. Now that's not surprising. Let's do a hypothetical example here. You sell an average of 100 gallons of milk per day. I ask you, how many do you think you're going to sell over the next 7-day week? You say, I know the average of 1 day's sales, that's 100. You're asking me what the total sales will be over a week, that's 7 days summed up. What do I expect that to be? I think everybody in class would simply say 7 days averaging 100 a day means the average sales over a week should be about 700. And that's correct. The central limit theorem tells you that's correct, which is exactly your intuition. So not too surprising, item 2. Item 1, quite surprising. Put it back into that example. How many gallons of milk do you think you will sell over the course of this week? Even if on a daily basis sales do not follow a normal distribution, when you ask how many are you going to sell over a week, that tends to follow a normal distribution, even though the daily demand doesn't. Finally, the most important thing perhaps of this outcome is not how the means behave, but how the standard deviations behave. It turns out that the standard deviations do not sum. You cannot say, what is the standard deviation of a week's demand? It is not 7 times the standard deviation of 1 day's demand. Instead, the standard deviations of a week demand goes by what we call the root mean square. So I'm going to write this down, and then we're going to see this in multiple examples. The standard deviation of the sum is not simply the sum of the individual standard deviations, but instead is the root mean square. Why does this matter? This is going to matter over time because what it tells us is the means grow linearly, but the standard deviations grow less than linearly. Or put in plain English, it's actually much easier to predict the sum of a bunch of random variables than it is to predict an individual random variable itself. Okay, so I agree, pretty mathematical. Right now, you guys have probably watched that several times or fallen asleep. But let me show you how this works out in a very simple example, and maybe this will explain some things to you. Let's go back to that trying to predict how many sales you're going to have of some kind of milk or something. And let me give you some data. Suppose we had historical data on how much milk the H-E-B stores in the Austin area sold on a daily basis. So let's take some data. Let's suppose the average daily sales, and I'll call that mu daily, is 1,000 gallons of milk each day. Now, you know, from statistics, we realize we may sell an average of 1,000 per day, but there's variation in that. Some days we sell more than 1,000, some days we sell less than 1,000, and the way we express variation is by standard deviation. So suppose we put all the data into Excel, I don't know, the last 500 days of demand, and we said, Excel, here are the last 500 days of demand. I want you to please calculate the average, which would be similar to the mean, and please estimate the standard deviation. And suppose the standard deviation were 600 gallons of milk. Now, if you remember your statistics and you remember the normal distribution, there's no way this is a normal distribution right here. Because in a normal distribution, if you take the mean and you go 3 standard deviations below the mean, and you go 3 standard deviations above the mean, you've encompassed roughly 99.7% of the possibilities. You can't go 3 standard deviations below the mean. What do you have? 1,000 down to selling nothing. And I have no idea whether you can go 3 standard deviations above the mean. The bottom line is, this is not necessarily a normal distribution, nor does it matter. So that's the data we have. And I would like you to predict 1 month's demand. Want to predict, let's call a month 30 days. 30 days of demand. Maybe this is how we order. We order 1 month's worth of stuff at a time. So I want to predict what the total demand will be over 30 days. And all I have is data on what the daily demand looks like. How do I do that? Well, is this a true statement? I'll call the total demand T. The total demand is going to be equal to, well, whatever the demand is of the first day in the month, plus whatever the demand is in the second day of the month, up to whatever the demand is in the 30th day of a month. We're trying to predict next month's demand. Isn't it true? It'll be however many we sell that first day of the next month, plus however many we sell the second day, all the way up to however many we sell the 30th day. So given that that's true, which it is, that's a true statement, this is starting to look an awful lot like an application of the central limit theorem. Let me have you look at the central limit theorem up above to remind you of what that formulation looks like. So if you look up above, you're going to see let x1 through xk be independent random variables. For the moment, let's assume that each day's demand is independent. I will explain that in a moment. Then, suppose we're looking for a sum. Y equals x1 plus x2 up to xk. Well, that's the sum we're looking at. T equals d1 plus d2 up to d30. Suppose we know what mu and sigma are for each day. We do. Each day has the same mu and the same sigma. I want to predict what t is going to look like. But if you look at this up here, this tells me that provided 30 is close enough to infinity, the sum is going to behave normally. Its mean is going to be the sum of the means, and its standard deviation is going to be the root mean square of the standard deviations. That is, the sum is normal, regardless of what the individual daily demand looks like. The mean of the sum is simply the sum of the means. The standard deviation of the sum is not the sum of the standard deviations, but instead is the root mean square. So let's apply this down below again. So, according to the central limit theorem, if two things hold, if 30 is close enough to infinity, which I'm going to tell you for all practical purposes it is. Our general rule of thumb in statistics is 30 items is close enough to infinity. Our general rule of thumb in operations is probably 10 is close enough to infinity. And if independent demand, if these two things hold true, then we have a very interesting outcome. T will be normally distributed, and the mean of T, applying simply the calculations we did above, is going to be the sum of the means. So I'll go sum I equals 1 to 30 of the means of each of those days. But remember, every day has the same mean, so this is exactly the same thing as saying mu of day 1 plus mu of day 2 plus mu of day 30. But all of those are the same. The mu of day 1 is simply mu daily demand. The mu of day 2 is simply mu of daily demand. All the way up to the mu of day 30 is simply the mu of daily demand. So I can simply say the mean of how many I sell is going to be 30 times the daily demand mean, which was 1,000, equals 30,000 gallons. Now, I don't think anybody's surprised by that outcome right there. If I told you, you sell an average of 1,000 a day, how many do you think you're going to sell in 30 days? You're going to say 30 times 1,000 equals 30,000. You probably wouldn't have known it was normal, which is what the central limit theorem tells you. But perhaps most importantly of all, the standard deviation of the daily demand is now known. And basically, according to the formula, it's the square root of I equals 1 to 30 of sigma I squared. But let's just do the same thing we did before and start plugging in. This is the same thing as the square root of, well, that's sigma day 1 squared plus sigma day 2 squared plus plus sigma day 30 squared. But remember, we all know sigma of each day is exactly the same. It's the sigma of daily demand squared. That's the same as the sigma of daily demand squared. All the way up to this is sigma of daily demand squared. So we can write this as the square root of 30 times sigma of daily demand squared. And we just keep on going. The square root of a product is simply the same as the product of their square roots. So it's the square root of 30 times the square root of sigma d squared. But the square root of something squared is simply itself. So we've got the square root of 30 times the 600 we used to have. So this went to 30,000 gallons, whereas this went to the square root of 30 times 600. So square root of 30 is about 5.47 times 600, and we end up with 3,286 gallons. Now, what does that tell us? This is interesting, because if I draw a normal distribution, and this axis is that uncertainty that I need to know, how many am I going to sell over the course of 30 days? So this is the value that T can take on, my total demand over 30 days. What I now know is, to a fairly high approximation, I expect to sell a normal distribution whose mean, mu of T, equals 30,000 gallons, whose standard deviation, I'm just drawing an arrow to that since there's no way to directly reference the standard deviation, whose standard deviation of T is equal to 3,286 gallons. I know a lot about how much I think I'm going to sell in 30 days by only knowing information about each day. And that's what's interesting about the central limit theorem. One last thing before we kind of wrap up our central limit theorem and talk about its applications. One thing that you should know is for a standard, for a random variable, the most important indicator of its predictability, how manageable is it, is something called the coefficient of variation. And for any given random variable, the coefficient of variation is written like this. The CV, or coefficient of variation, is simply equal to the standard deviation divided by the mean. And this is going to range between 0 up to a big number. And the smaller the number, the more predictable the random variable. So check something out. If I look at the coefficient of variation of the original data, the coefficient of variation of daily demand is the standard deviation of daily demand divided by the mean of daily demand. That's 600 over 1,000 equals 0.6. 0.6 is not a particularly easy to manage random variable. That's a 60% coefficient of variation. The standard deviation is 60% of the mean. This is difficult to manage. But look at what the coefficient of variation of 30 days worth of demand is. That's going to be the standard deviation of the total demand divided by the mean of the total demand. And we just established the standard deviation of the total demand is 3,286, whereas the mean of total demand is 30,000. And when you take that ratio, you get about 11%. And interestingly, an 11% coefficient of variation, where the standard deviation is only 11% of the mean, is actually pretty easy to manage. Most tools work well. And this is what the central limit theorem helps us to understand. Provided certain conditions are true, namely, you've got enough data points that are close enough to infinity. For our purposes, 10 or bigger, certainly 30 or bigger works, and independence, we'll come to that one. Provided those things are true, the sum of random variables is actually much easier to predict and work with than individual random variables.